Hey, let's take a look at a shortcut way we can use to find work. Now we know we're going to define work as the vector field dotted with the displacement vector dr. So let's say we have this vector field mn and we're traveling on this path. Whoops, my path disappeared. There we go. We're traveling on this path r, which we're going to define parametrically as x of t, y of t. So we're going to show another way we can write our work equation, or our vector field on our line integral of a vector field. So to write this, if I were to rewrite this, the f and dr, I would get my work would be the integral f, which we're saying m n, and we're going to dot that with r prime, or dr, where I can get dr pretty easy. Dr would just be the dx dt, dy dt. Remember, it's really dr dt, and I can just multiply and get the dt over here. And that's going to give us this dx dt, dy dt, dt. When we take the dot product, we are going to get m dx dt plus n dy dt, dt. Now, so here is my work equation. Now notice I have this dt on the outside here, and if I can distribute that through, they're going to cancel out here. So we can now define work as the integral of m dx plus n dy. Why is it so nice? Well, I can actually now break this up into component forms using my change in x and my change in y as the following. The integral of m dx plus n dy. That line integral. And these are all line integrals, so I guess I should put my little c's down here. There we go. All right. And this is actually sometimes can make it a little bit easier for us to integrate because we only have to look at the component parts. So let's take a look at an example. So here's our rule right up here. Here's our rule right here. Line integrals in differential form is just another way to express and evaluate a line integral of a vector field. We can abbreviate our notation to the following forms to speed up the process of evaluating integrals. So again, we can take the line integral of our partial with respect to x dx. Remember, how do we get m? Remember, when we look at our vector field, remember it was a partial of x, partial y, so on and so forth. Well, that's our m, that's our n, and if we go to 3 dimensions, that's p. So this is our partial of x with respect to x, and that's our partial of y with respect to y. So we only have to look at with their corresponding variables. Now, once we have our rule right here, so this is my work equation, and in 3 dimensions it would look like this, or my line integral would look like this. We can either convert the variables into parametric or leave them the same variables depending on the problem itself. So let's take a look really quickly at question number 4. We want to evaluate the line integral y dx plus x squared dy. Oops, sorry about that. Again, these are just our set of partials right here, where our curve is this parabola from 0, 4, 0 to 1, 3. Now, notice everything's in terms of dy and dx here, and so is my path. So I don't need to convert this to a parametric if I don't want to. So to solve this one right here, I can just plug everything in. My first line evaluating integral would be this y dx. Well, what is y equal to? That's just this 4x minus x squared dx. Plus, and now I'm going to do the line integral for the y. Remember, we can separate these out. My line integral for x squared. Now here is a problem, but I don't want to evaluate x squared in terms of y. I want this to be a dx right here. So I have 2 options here. One, I can easily solve. I can solve this one for in terms of y, which is not so pretty. Or I can just look at the derivative. So in other words, if I know y is equal to 4x minus x squared, I can find dy by taking the derivative 4 minus 2x dx. And that's what I'm going to multiply here. 4 minus 2x dx. Alright, so what we can do now is, notice everything's in terms of x. And now I can get my domain super easy here, because remember my points are going to go from 4, 0 all the way to 1, 3. Well, if everything's in terms of x, my x starts at 4 and goes to 1. So my domain, my x starts at 4, so I can scratch out this, make that a 4, and goes to 1. I'm starting at x equals 4 here, and I'm going to 1. And this right here I can use to solve my work equation. Looking down below, let's take a look here. In this last example, our path is this parametric. So we have a parametric path here. Our interval, 0 to 2 pi, so there's our time interval. And we want to evaluate this line integral. Now notice my path is parametric, but everything's in terms of x and y. So for this one, yeah, we're going to have to do a little bit of converting right here. But it's not terribly bad. Ready? I know x is equal to this 3 cosine of t, and y is equal to 3 sine of t. So far, not too bad. Everything looks pretty nice. But I also have to convert my dx and my dy's. Ugh, that's the problem. Messier. So my dx is just this negative 3 sine of t dt, and our dy is 3 cosine of t dt. And now when I write my integral, again I'm going to split this up. Looking at my y cubed just becomes 27 sine cubed of t times dx, which is this negative 3 sine of t dt. So there's my x's. Now for my y's, I need x cubed, so that becomes 27 cosine cubed of t plus 3 times x. That's this, 3 times x, sorry, messed that up. X was this 3 cosine of t times y squared, which becomes 9 sine squared of t. And all this, ready? And now I need my dy, which was this times 3 cosine of t dt. Oh, that looked out pretty nicely right there. And you can solve this by hand if you hate yourself. So I think it turns out not terribly bad. Now, so t here, my t goes from 0 to 2 pi, so I just put my domains here, 0 to 2 pi here, and 0 to 2 pi here, and that will evaluate it for our work problem, I think. I hope you enjoyed the videos and all the wonderful interruptions there were, and I will see you all later. Bye-bye.